So you guys probably have figured this out already, but what you might be wondering is, why would you go to all that trouble? Why would you care to make anything private? And the answer is reasons of good software engineering. And software engineering, both when you're building large software programs out of multiple components, and moreover, when you're working in a team with other people, and you want to make sure that the work that you're all doing together can be broken down in a way so that the interfaces between your code and your partner's code are simple. And so here's a few more specific answers. First of all, you want to prevent the data in your class from being corrupted by other classes, which might be written by your coworkers or by you on a bad day. Second reason, by keeping certain things private, you can ensure that other classes won't come to depend on those things because they can't even see them. And so if you want to go back later on and change the implementation of your program, you can do that. So I want to give you a simple example of this using dates which you're already familiar with. So here's a simple little date class. And I've made it really simple. I've just got a day and a month in it. But you'll notice I've declared the day and the month private. And I've got a little helper method called setMonth, which is used for internal purposes. And I've also declared that private. So those methods are not accessible from outside the date class. And now suppose that, before I mention that, of course there are some public methods like the date constructor, but the date constructor is something that you want to provide as a service for other classes to use. So you make that public, and you also make sure it has error checking codes so that if other classes try to abuse your class, you can catch them. Now imagine, now that you've declared these things private, that somebody else, maybe in the same company that you work for, writes a class called Evil Tamperer and tries to tamper with your stuff. Well, they will be able to create dates normally, but if they try to fiddle with the internals of your structure, like for instance if they try to change the day in one of your classes directly, then, well, you've declared that private, so this is not going to work. Java will refuse to compile this. And likewise, if you try to call a method that was never intended for public use, then Java will refuse to compile that. So this is the advantage you gain by declaring all of your vulnerable parts private. You guys have dirty minds. I approve. Now, the reason why this is an advantage is you might want to come back because you might tomorrow think up a better way to implement the date class. And your new better way of implementing the date class might not even have a day variable. Maybe you've decided that instead you're going to encode the day in a neural net or something like that. And you might not need this set month private method anymore, so you get rid of it. Now, if you had allowed your coworker to write this into their code, these lines of code that depend on how you have internally implemented the date class, you would never be able to go back and improve the date class in any significant way. You would be pinned down to supporting that particular way of representing a date forever. And so that's the real reason why you use private a lot, is so that you give yourself flexibility, especially when you're working in a large software team with other people, to be able to improve your implementation in the future if you come up with a faster algorithm or just a better way of doing things, something that takes less memory, whatever. Any questions about that before I start getting into details? Yes? Can you give them partial access? So they only have a limited number of times to change a variable, is what he's asking. And no, Java doesn't provide a way to do that. So, yes? Other paradigms? Well, you don't necessarily have to have object-oriented programming to do this, although this is kind of something you mainly find in object-oriented languages. So I would say that for the most part, you should think of this as something that's one of the advantages of object-oriented programs. Yes? All right, so now I'm going to give you some software engineering definitions. I'm just going to throw them at you now and try to explain them a little bit. I think that these things will come clearer as we see examples of them throughout the semester. So don't worry too much if this is not 100% clear now. But these are the things that, sort of the main software engineering concepts that we need to understand in this class and try to learn this semester. First of all, the interface of a class is basically made up of two things. It's a set of prototypes for public methods, like, for instance, in the date class I just showed you, we would include the prototype for the date constructor, which is public. We would not include the prototype for getMonth, which is private. And by the way, I hope you all learned what the word prototype means in discussion section. If not, ask your TA for your money back. But an interface is made up of two things. One is the prototypes for the public methods, and occasionally the public fields, plus descriptions of those methods' behaviors. And those descriptions are in plain English. So what an interface really is it's instructions to your programming partner, or to yourself at some time in the future when you forget how your code works, of how to call your methods. And the interface is the part that you make public and advertise to the world and say, here's my great date class, here's how you call it and use it. Now, some kinds of classes are special kinds of classes called abstract data types, which is kind of an official computer science word, and it's got so many syllables that everyone just calls it an ADT. And that is a class. Well, usually it's a class. I'm being vague here because sometimes an ADT is made up of several classes. That has a well-defined interface but its implementation details are hidden. They are firmly hidden from other classes. Why are they hidden from other classes? Well, so that you retain the flexibility to change your implementation later on. Your clients can't snoop in the internals of your ADT and thereby lock you into one particular way of implementing it. So the date class that you guys implemented for homework 2 is an example of an ADT if you programmed it right. And we'll implement a lot of ADTs this semester, so you'll get used to the idea. One of the cool things about ADTs that really helps you reason about your programs and build huge programs that actually work is that an ADT allows you to enforce invariance. And an invariant is a fact about its data structure, well, specifically about how it is represented internally. That is always true, assuming that your code doesn't have any bugs in it. So, for instance, the date class enforces an invariant. It enforces the invariant that a date object always represents a valid date. You programmed your date class to make it impossible for an outside class to come in and construct a date object that refers to an invalid date. And so this sentence is an example of an invariant. And knowing that that invariant always holds and that your data structure enforces that invariant lets you relax. You don't have to think about that anymore in figuring out what's going right or wrong with your program. Now I want to mention that an ADT is a good thing to aspire to a lot of the time, but there are classes that are not ADTs, and people when they first learn about it sometimes get carried away and try to make everything into an ADT. But sometimes you will define a class whose only function is to store data. And in that there are no invariants. There's no particular constraints you want to enforce on that data. It's just a way of passing numbers around or something like that. If you've looked at Project 1, then there's an example of that there. So let me write this down. Not all classes are ADTs. Maybe most of them are, but you actually have to think about it first. Some classes are just data storage units. And if there are no invariants really worth enforcing, then you generally don't need to define an ADT. You can just make everything public and not work hard. So, one thing I should have mentioned, for those of you who haven't been reading the news group, I want you to know that Project 1 is available. So is Homework 3. Homework 3 is due in a week. Project 1 is due in 2 weeks. Homework 3 is a little exercise that's actually designed to give you some practice for a harder thing that you have to do in the project. Project 1 will be a lot of work, so please start now. It's an individual assignment. And I just want to mention that there is an example in this project of a class called type and size. And when you look at it, this will be sort of your classical example of a class that is not an ADT. It's just used to store data. In fact, its sole purpose is to give us a way of returning 2 ints from a function instead of just 1. Any questions about any of this before I give another example of an ADT? All right. Here's a list ADT. Well, actually, we saw some of it already last lecture. We saw most of it last lecture. But what I want to point out now is that I designed it so that it's an ADT. And I showed you some advantages of having an S-list class instead of just having list nodes at the end of last lecture. I want to add another advantage of having a separate S-list class and not just having S-list nodes by themselves, is that you can enforce invariance. The first invariant is that the size field is always correct, which is a shorthand way of saying that size is always equal to the number of items that you can get to starting from the head pointer of the S list and following a chain of next pointers. And number two, a list is never circularly linked. What do I mean by circularly linked? Well, if I had a list that looked like this, that would be an example of a circularly linked list. And you can see that this is a problem because if I try to, for instance, print all the items in the list, my loop might keep walking forever and never stop. So that's not a good list representation. Did you have a question? Well, if you could allow a list to be circularly linked, then yeah, it would look like it was infinite. And that's another reason why we're not going to allow it to be circularly linked. So you'll notice that these invariants are not statements about things that calling routines see. They are statements about the actual implementation and the internals of the data structure that we are trying to hide. But they're still important for reasoning about a data structure and how it works and proving that it's correct, things like that. So when I say a list is never circularly linked, another way of saying that is if you follow the list, eventually you will get to a node whose next pointer is null. So that's another way of expressing that invariant. Both of these goals are accomplished through a few simple Java mechanisms. So one way to look at it is that only the S-list methods can change the lists in any significant way, or can change the list's internal data structures. So if one of your coworkers uses their evil tamperer program to try to change the internals of your list without going through your S-list class, they can't do that. By the way, you guys might be wondering, am I saying that if you go to work at a real-world software company in a project team, that you will actually come to see your fellow coworkers as evil tamperers? Yes. That is exactly what I'm saying. You will. You think I'm joking. I gather we have a few people here who've had this experience. So how does S-list ensure that only S-list methods can change your lists? Well, first of all, the fields of the S-list class are private. So no one Your coworkers can't just go in from their methods and change head and size. And second of all, the individual nodes cannot be tampered with because no method of slist returns an slist node. So there's no way that an external class can get its hands on a reference to a node in a list. It can get the items out of the list, like the objects, but not an actual list node. And so these two invariants together ensure that size is always correct. The second invariant ensures, the second fact here is what ensures that invariant 2 is always correct, because no one can go in and tamper with your list nodes. Any questions about that? Yeah? Right.
Access it to know the actual value?
Well, unfortunately, Java does not give a way to allow you outside classes to be able to read a field without being able to write it. That would be a great convenience if Java had that, but it doesn't. So instead what we do is we write a method that returns the size field if we want to provide that service to outside classes.
There's no way to use the dot size. You have to do size.
Right. So you need to write a size paren method and have it return the size field. And make that size method public. All right, so that's S-lists. Next I want to talk about D-lists, which is my name for what's called doubly linked lists. I'm going to give you two versions of doubly linked lists, but as we saw last class, if you want to insert or delete an item at the front of a list, it's easy. Like, for instance, I showed you inserting last class. Here's code for deleting. In an S-list. So delete will do nothing if there's nothing in the list. But otherwise, if there's at least one item in the list, then we just remove the head by making the head pointer point to the second item in the list. And then we say, okay, we've just reduced the size of the list by 1, and we're done. Easy, right? But maybe we want to insert or remove an item at the end of a list. That's not so easy. Question? Java takes care of garbage collections. The node we just removed from the list will probably disappear, unless something else is referencing that same list node for some reason. Whenever the garbage collector has time, basically. One of the nice things about garbage collection is you don't really have to think about it. You don't have to worry when items disappear. It doesn't change the way your program operates. All right, so let's look at inserting or deleting an item from the end of a list. Well, basically, you don't have a pointer to the end of the list generally, so this takes a long time. You have to start at the front of the list, walk all the way to the end of the list, and then insert or delete. And if there's a million items in your list, then you've just wasted a lot of time. Now, in Lab 3 next week, you'll see that by adding a tail pointer that points to the last item of the list, you can solve the inserting problem. And then it becomes easy to insert at the end of a list. But deleting is still hard because there's no way to back up the tail pointer. So when you want to be able to delete at both ends of a list, that's where doubly linked lists come in really handy. And so here's I'm going to just leave out the public since it doesn't really matter right now. And give you a quickie doubly linked list class. Version 1. Okay, so a doubly linked list node is like a singly linked list node, except it has references to the next node in the list and the previous node in the list. And our totally basic dlist class is going to have a head pointer that points to the first item in the list. But we also want to be able to insert and delete at the end of the list, so we're going to have a tail pointer too. So that's the definitions. Now let's draw what these things actually look like. All right. Here's a list with 3 items, and the items are 4, 1, and 8. Okay, really the items should be references, but I want to get this drawn quickly, so I'm just making them ints for now. So that's how the list nodes are connected together. They have next pointers as usual, and they also have prev pointers that points to the previous item in the list. Yes? For now, we want it to be null. It can't, I mean, this is the head, actually. Well, it can't point to the dlist because it's of type dlist node. So for now, or for version 1, yeah, we're just going to leave those null. And then here's our actual dlist. Has a head, has a tail. So now we can insert and delete items at both ends. In constant running time. Per deletion or insertion. So, just to show you an example, here's code that removes the tail node. If there are at least 2 items in the dlist. And it's nice and simple. It just takes 2 lines. well, two kind of maybe a little bit complicated looking lines. So let's execute these lines and see what they do. Since I've got all these dots in there, maybe it's worth taking a quick look. So this is all running from inside the dlist class, which means this tail is the tail in the dlist object over there. And so what does the first line do? Well, first it looks up the tail, and it follows the tail, and finds whatever the tail is pointing to. And then after tail, it says .prev, so we look up the prev reference inside the tail, and we follow that reference wherever it goes. And then it says .next, so we find the next field inside there. Except we're not going to follow that reference because this is an assignment. We are assigning a new value into this box. And the new value that we are assigning is null. So what we've just done is we've cut off this pointer because we are removing this item 8 from the list. This is going to be the new tail of the list, and since it's the last item in the list, it should now have a null pointer in its next box. So that's the first line of code. The second line, well, we find the tail, and so we are going to change what's in that box and assign something else to that box. What are we going to assign? Well, first we're going to follow the tail, the old value of tail that hasn't changed yet, see where it points at, this object here. Then .prev means we look up the prev field, and whatever's in that box, we copy into this box. So there's your new value there. And so now you can see that the list is like a little clique of playground buddies who aren't willing to play with this node anymore. This node still wants to play with them, but it doesn't matter. This pointer is irrelevant. For all intents and purposes, that node is out of the list. All right. So I just said this removes the tail node if there are at least two nodes in the dlist. Oh, question?
Sorry, is it better to have the pref not point back? Because later when you remove item 1, it won't be garbage collected because it's still
Well, this node will get garbage collected because nothing points to it. And the other nodes will not be garbage collected, but they shouldn't be. Yes? No. No, garbage collection only looks at who's pointed at. It doesn't look at who's pointing. So again, I said that this code works if there are at least two items in the dlist. But if there's no items in the dlist, you need a special case to handle that. And if there's only one item left in the dlist, you need a special case to handle that. So I want to look at a way to simplify a dlist that simplifies the implementation a little bit. And it just makes for a more elegant dlist structure in a way. The idea is that we're going to designate one special dlist node to be something called a sentinel. A sentinel is a special node that doesn't actually represent a data item. So I'm going to show you a new dlist data structure, similar to the old one but different. Dlist version 2 is going to be a circularly linked, doubly linked list. Our sentinel's job is going to be to represent both the head and the tail of the dlist. So let's make some changes here. I'm not going to change the dlist node, but the dlist doesn't have to store a head and a tail anymore. Now it just stores a pointer to the sentinel, which I'm still going to call the head, even though I'm changing the meaning of head. But now the head is going to be the sentinel, which will not store an item. And since I want to have a nice complete data structure, I'll throw in the size field now too. So this will be a dlist that I can be happy with. The sentinel is just another dlist node, like these ones here. But its prev pointer points to the tail of the list. And its head pointer, its next pointer, points to the head of the list. And that's how we know who the tail and head are now. And the item is going to be whatever, a null pointer. Because we're not actually storing any item there. But it doesn't matter what we make that field, because we will never look at it. Another change that this allows us to make, and this is one of the reasons why this data structure is going to be slightly more elegant, is because there will no longer be any null next fields. The next field of the tail will point to the sentinel. And there will be no null prev fields anymore. The prev field of the head will point to the sentinel. And then, of course, you still have your dlist, but now the dlist just points to the sentinel and also stores the size of the list, which is 3, not 4, because you don't count the sentinel, because the sentinel doesn't store an item. And the sentinel is a hidden part of the data structure. Since this is an abstract data type, none of your users should ever know whether your dlist uses a sentinel or not. That's supposed to be hidden. Any questions about this? All right, now that we've got this dlist with the sentinel, we can write down some invariants for it. And it's actually got quite a few invariants. The sentinel makes those invariants a little bit simpler, actually, than they might have been with the original dlist version 1. So, first of all, the way that we store our dlist data structure, the head is never null. Because there's always a sentinel node. Even an empty dlist will have a sentinel node. Second of all, dlist nodes cannot have next pointers that are null. There's always got to be a next node in the list. It might be the sentinel, but there's always a next node in the list. There's always a previous node in the list. I also want to have invariants that make sure that if I think you're in front of me in line, then you think I'm behind you in line. Otherwise, one of us is obviously very confused. So, if x.next is some other dlist node y, then y.prev points back to x. And of course, this relationship should go both ways. So whoever's behind me should also think I'm ahead. And 6, the size field is always correct. Which means it's the number of D-list nodes in the list, not counting the sentinel. Again, remember, sentinel is an implementation detail that should be hidden by your abstract data type. No one should know whether your D-list uses a sentinel or not. So we're certainly not going to count it. The full way to say this invariant is that the size variable is the number of D-lists, not counting the sentinel, that can be accessed from the head of the list through a series of next references. Finally, how do you... Oh, question here?
So in an empty list, sentinel will function itself?
That's right. In fact, that's just what I was about to write down. In an empty D-list, the sentinel's previous and next fields point to itself. So, no doubt we'll have a homework where you actually construct one of these empty D-lists yourself. And a lot of you are going to get this line of code really, really wrong because you should use more than one line of code for it. You might recall that I said earlier in the semester that, or a few classes ago, that when you have an assignment where some value appears twice, that this is the old value before the assignment, and this is the new value after the assignment. This is something that you will want to make sure you remember when you are writing code to create a sentinel that points to itself, as many of you will discover and struggle with in the coming weeks. That's a hint. It's not the full answer, but I figure you should have a hint. And that's all I have to say for today. Any more questions? What's that? Can I repeat the hint? The hint is, if I have an assignment statement in which a reference appears twice, this is the old value of the reference. This is the new value of the reference. If you don't remember that, and you try to write code that creates a new sentinel whose next and previous pointers point to itself using the obvious constructor, then you might make a big mistake and spend several hours wondering why your code doesn't work. I see it happen every year, so